Basically what this hypothesizes is that there is kind of a hypothetical state that exists in between the reactants and products where you start to see the reactants bonds being broken and the products bonds being made, but they are not fully done on either side. Okay, so there's not a full breaking or a full making. There is in between of both. To crystallize a transition state or to actually see that it exists is actually really hard. It's not an easy thing to do and has only been done a little bit over time. So just FYI, this is really a hypothetical state. It's not something that we're going to see that's going to be made that's stable in any way, shape, or form. This is an unstable intermediate. And it is often shown with a double cross, right? So basically, this kind of symbol where you have kind of the sense of something's being made and something's being broken. It's kind of how I think of the two lines across. Okay, how do we see transition states actually in things that we conceptualize, right? In chemistry? Well, the most common place we conceptualize transition state theory, I should say, is with energy diagrams. So what we're going to have here is we're going to have the reactants. And I'm going to start off with the products right here. And we're going to talk about a one-step reaction. Okay, so when this reaction happens, it doesn't just go from reactants to products. Okay, the energy between the reactants and products is actually the delta G of the reaction. All right, so it doesn't just go from reactants to products, it actually goes through a transition state. And that transition state is the highest point of the graph. Whatever you're looking at, this diagram has to have a high point. The high point is that transition state. The idea here is that all reactions undergo kind of what we would think of as like a roller coaster, right? So they pretty much go through this beginning piece. The very first part of the roller coaster is getting up to the top, right? So you're going up, 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 up. That's what this is, okay? And then as soon as you get to the top, it's a free fall, okay? And most reactions are just going to free fall. Even if they have to go up again, it's still going to be in the midst of this free fall. All right, so in this case, what is this right here? What that is that's the amount of energy it took to get to the transition state. And that amount of energy is called the activation energy. It's the amount of energy to get to activate the reaction. Or sometimes people will call this not a transition state, but they'll call it an activated complex, which is yet another way to talk about the transition state. Hey, all of these terms are basically very much the same kind of idea, right? So activated complex, for all intents and purposes for us, is going to be synonymous to the transition state. Same thing. Okay. Activation energies are fabulous. This is the amount of energy it takes to make this reaction happen. And I can tell already in this reaction that this is a one-step process, and that the amount of energy that it takes to activate the complex is actually much more than I'm going to get out of it in the end. Okay? What this would probably end up being is end up being, yes, a spontaneous process, but it may not happen very easily just because of this high activation energy. So what do we throw in when we have this kind of occurrence? What we throw in at this point is we throw in a catalyst, and we say, how do we make this one-step reaction better? And the way we make it better is we no longer have a one-step reaction, we have a multi-step reaction. I'm going to draw over this. Okay, so what does a catalyst do? A catalyst breaks a reaction that has a very large activation energy, or that maybe have an insurmountable activation energy, into pieces, right? So instead of having one hump and knowing this is a one-step reaction, they call these hills, by the way, instead of humps. Instead of having one hill and therefore a one-step reaction, we now have three hills, and that is a three-step reaction. It's a multi-step reaction, right? And so what do we have here? What we have is we still have the delta G is exergonic. This is still the delta G of the reaction, okay? We still know it's an exergonic reaction, but now look what's happened. What's happened is instead of having an insurmountable activation energy, I cut that way down, okay, for the first step. So this would be an activation energy associated with step 1. This would be the activation energy associated with step 2. And this would be the activation energy associated with step 3. Okay? Now, what's really interesting is that biology spends a lot of time talking about how a catalyst decreases the activation energy of the reaction. I don't know many catalysts that actually do that very well. Okay, so in other words, what happens here, and I worked for I worked for a mechanistic enzymologist who had a real beef with this. So, you know, give me a moment here for all of you biologists who are having a hissy fit, or biochemists. Okay, it's not that it decreases usually the overall activation energy. It's that it breaks it into steps such that the slowest step now has a smaller activation energy than it did. Okay, so in other words, if I call this the activation energy of the overall reaction, then usually the activation energy of the overall reaction is going to be equal to the activation energy of 1 plus the activation energy of 2 plus the activation energy of 3. It's not that it that it really decreases. It might lower it slightly, but not overall, really. What it does is it makes it much easier to get to the top of the roller coaster, so that your slowest step, which is the one with the highest activation energy, is much more overcomable, right? You can get to the top of that roller coaster. And once you hit the top of that roller coaster, then you're just free falling. And even if you have to go back up, which is what we're essentially saying here, you have the momentum built to be able to do that. That's basically what a catalyst does, okay? The best catalysts we know are the ones that, well, are really recyclable ones, right? Ones that are used in the first step and then remade at the end so that you can use them over and over again, okay? Okay, the idea here is that with reaction intermediates, those are actually stable products that are made in one of the steps. So, in terms of this, you have 3 transition states, you have 3 activation energies. The slowest step is the first step because it has the largest activation energy compared to the other 2, and you have reaction intermediates as well. All of this is to say that multi-step reactions have lots of different transition states. And remember, I can tell that this is a 3-step reaction because it has 3 hills.
Let's talk about EEG, something that may be distantly familiar to you. EEG stands for electroencephalogram. Bless you. Electro refers to electricity, encephalo refers to the brain, and gram refers to something written. So together, an electroencephalogram just refers to something that measures electricity in the brain and records it. EEG can be recorded from electrodes outside the skull, non-invasively, or from electrodes being placed inside the brain by a neurosurgeon, highly invasively. This video will focus on scalp EEG. So how could this technology actually work? EEG exploits something called a dipole. A dipole is two different charges that are separated by a distance. So if we stick electrodes, bits of metal that conduct electricity, here and here, we can generate a readout of the difference in charge between these two areas. So why does your brain have areas with different charges? Hold my beer. Your brain is one big electric circuit board made up of neurons. Interestingly, for a neuron that's resting, the inside of the neuron has a negative charge relative to outside the neuron, about minus 17 millivolts. Neurons can communicate with each other by neurotransmitters diffusing across this space called a synapse. Once neurotransmitters reach the next neuron, they bind to receptors where one of two things can happen. Something called an excitatory postsynaptic potential or something called an inhibitory postsynaptic potential. What are those? An excitatory postsynaptic potential is where neurotransmitters binding causes positively charged particles, called ions, to flow into the neuron, making the inside of the neuron more positive. This makes this area, the extracellular space outside the neuron, relatively more negative. Because this area is now more negative, the distant extracellular space at the other end of the neuron becomes relatively more positive. This means we have two different charges separated by a distance. We have a dipole, but it's also possible to have a dipole the other way round from an inhibitory postsynaptic potential. Here, the neurotransmitter binding causes negative ions to flow into the neuron, making the inside of the neuron more negative, making the extracellular space relatively more positive, making this distant extracellular space more negative. So excitatory postsynaptic potentials and inhibitory postsynaptic potentials create differences in charge, dipoles, at the opposite ends of the neurons. But the dipole for a single neuron is really small and not fabulously detectable. But luckily, in the cerebral cortex, just below the scalp, there are billions of large neurons that lie parallel to each other, perpendicular to the scalp. Apologies for the less beautiful drawing, but these large neurons are called pyramidal neurons. Clusters of these pyramidal neurons are usually stimulated together, giving them individual dipoles, which summate to form a larger charge just below the scalp. Now we have this area of the brain being one charge and this area of the brain being another charge, a larger detectable dipole. So we can stick an electrode here and here and measure the difference in charge between these two areas. This is exactly what an EEG signal is. It's the electrical difference between a pair of electrodes on two different parts of the brain, created as a result of clusters of pyramidal neurons being excited and inhibited. A typical EEG sees 32 electrodes placed over the brain, and we need a way to pair up these electrodes. How do we do this? One approach is to compare every electrode to the same electrode. This produces something called a common reference montage, where each horizontal line shows the electrical difference from each electrode to the same electrode. This can be identified from the left-hand side of the montage. Another approach is to compare every electrode to the electrode next to it. This produces something called a bipolar montage, where each horizontal line shows the electrical difference from each electrode to the one next to it. Both of these approaches, and some others, are incredibly useful for understanding brain activity. With lots, like years of training, you can learn to notice certain patterns in all of the squiggly lines. Just FYI, I most certainly don't have this ability. You can look at the amplitude of the signal, which is how much it goes up and down from this midline. You can also look at the frequency of the signal, which is the number of waves in a given amount of time measured in hertz. EEG patterns are commonly described in terms of the frequency of the signal with 5 key bands. Sleep produces delta waves, which have a frequency of up to 4 Hz. Deep relaxation produces theta waves, which fall between 4 and 8 Hz. Passive attention creates alpha waves, which are between 8 and 13 Hz. An active mind shows beta waves, which are 13 to 35 Hz. And high concentration or problem solving can produce gamma waves above 35 Hz. There's also an emerging area of research using machine learning and deep learning to analyze EEG montages.